The outline of my talk. First of all, we will discuss briefly about the path of transistor. Then I will discuss about the type of transistor. We will discuss about the Moore's law and evolution of transistor. That's the area where I'll give full stress or try to generate the knowledge. Okay, and then comes the more than more concept. We'll discuss about the various concept that is emerging, and from that we'll continue with the emerging nanoscale transistors. So what are the emerging nanoscale transistor? What are the trends? What are the recent trends? We'll discuss about it, and then finally I will conclude this lecture with some few references. So this is the outline or the brief of the of my talk. So transistor, you know that importance. It is the notably probably the most important invention since of the 20th century, and it has a pervasive role in today's world. Everywhere there are transistors, so they are everywhere you can find the IC or integrated circuit, and transistor is the basic building block of IC. So in this age of information age, we call it as information age. So in this information age, in PC, cellular phone, iPod, PDA, everywhere there are transistor, and already this transistor has already replaced vacuum tubes. So what are the coming things that we'd like to know? So there is no doubt about it that it is the most important invention of the 20th century. And the story behind this invention is one of the clashing egos and top secret research. We'll discuss about it slowly or briefly. So this is the importance, and then we'll briefly see the timeline. Okay, how it changes before going to the actual talk or actual that scaling approaches. I'll try to discuss the invention slowly or briefly. So first, I'll click the year 1874. In 1874, Ferdinand Braun discovered rectification. So this is the thing that crystal can conduct current in only one direction under certain condition. So that thing was discovered by Ferdinand Braun. Then in 1883, Thomas Alva Edison, he has invented the thermodynamic emission, where the flow of electron from the metal caused by the thermal vibration energy or the heat to overcome the electrostatic forces that holds the electron to the surface. So to overcome the electron that holds the electron to the surface, so overcome that force, we can apply the heat. So that is called thermodynamic emission. That is an important invention. And then in 1895, Marconi sent a radio signal over a distance. So over the Atlantic, he has sent a radio signal from one place to another place. And at the same time, I would like to mention that our own Dr. J.C. Bose, he has discovered the same, but a little bit unfortunate, or it was a story also that he couldn't get that Nobel Prize. So it was discovered in 1895. Then in 1898, J.J. Thomson discovered the electron, that famous gold foil experiment. In 1906, that Lee De Forest, who have discovered this vacuum tube, that triode, where there is a filament or cathode, which is the source of the electron. It ultimately goes to the anode or the plate through the grid, which is the control terminal. So basically, from cathode to anode, electrons are passing, and the controlling terminal is called grid. And this is the basic structure which has been followed in case of a transistor also. In case of a BJT or bipolar junction transistor, the role of the cathode has been replaced by the emitter. The role of the anode has been replaced by the collector, and the role of the grid was replaced by the base terminal. And in case of a MOSFET also, the same thing has been done. In this case, the cathode has been replaced by source terminal, and the anode has been replaced by drain terminal, and the grid has been replaced by the gate terminal. So, but the triode, with the major problem with the triode, it is big, unreliable, uses a lot of power. So that is why later the triode has been replaced by solid state technology or IC or transistor. In 1928, Linenfeld, a person from called Linenfeld, Edgar Linenfeld, he has filed a patent before which has been later, we will call it as a transistor. In 70s, these things will be actually fabricated. But before that fabrication, the idea was initially given by Lilienfeld in 1928. So he proposed the basic principle behind the MOSFET of a transistor, and he filed a patent. So that is the Lilienfeld who first proposed the idea of the MOSFET. That is in 1928. In 1934, Marvin Kelly, Bell Labs director, he felt that to provide the best phone service, you need a better amplifier, and the answer might be lying in the semiconductor. So he formed a department dedicated to solid state science, and that is the starting of the solid state engineering or solid state devices, we can say. So it is the Marvin Kelly of the Bell Lab who started this solid state devices, or called a separate subject also later, that solid state sciences. That is in 1936. In 1945, the Shockley, the team leader of the solid state department in the Bell Lab, hired Breton and Bardeen, and they discovered the first semiconductor amplifier relying on the field effect. So his device was a small cylinder coated thinly with silicon, mounted close to that small metal plate. আমি একটু পরে ফোন করছি, হ্যাঁ। Okay, that device didn't work, and the Shockley assigned Bardeen and Breton to find out why that didn't work in 1945. In 1947, Bell Labs unveiled the transistor, and they decided to name it a transistor instead of a point contact solid state amplifier. And John Pierce invented the name, combining trans resistance with the ending common to devices like varistor, thermistor. So that was the trend at that time. The devices are named after like varistor, thermistor. So in that sense, trans resistance, and with that terminology, they have called it transistor in 1948. In 1950, that Bell Labs was received a license from the Sony to build transistor, and for radio, actually Sony used it. Sony has given the order, and Sony has given the order for mass consumption for making or building transistor radio. So in the United States, they use the transistor primarily for computer and military purpose, but later it has been used for radio, transistor radio. So in 1955, the Shockley Semiconductor, sowing the seeds of Silicon Valley, they have first started the concept of Silicon Valley, and means basically they have started an area which will rely on the silicon devices and research, manufacturing, etc. So that is called Silicon Valley. That is the first idea behind the Silicon Valley. In 1957, that is a famous year, main year, the traitors ate abundant Shockley, founding Fairchild Semiconductor. So that is in 1957. And in 1955, that was, I have already told. And 1958, that is a famous year also. In this year, Jack Kilby of Texas Instruments invented the first IC. So it is named as JK flip-flop. So it is named after Jack Kilby. So it is the first integrated circuit made in the history of the world. So the idea was basically to accumulate or to integrate all component, passive and active, all components together in a single chip. So that is the first IC he has made. And in that figure, you can see the Texas Instruments first IC. In 1968, the Noyes and Gordon Moore, two of the traitors ate together with Andy Grove, formed the Intel Corporation, which was later became the biggest company of the world in the case of it. So this is the pictorial history of transistor. In 1941, you can see the vacuum tube. In 1948, you can see the point contact. In 1955, you can see the transistor in a coated tin coated package. And in 1957, it's another transistor. In 1967, see the IC has become, and 1997. So many transistor was put in a single chip, and that is the basic transistor area. Okay, so this has been already discussed. These things I have already discussed. In 1947, this is the transistor first picture of the transistor, point contact transistor. You can see the spring, you can see the collector, emitter and base. But this transistor was made up in the germanium. It is not a silicon transistor. So it is a first point contact transistor based upon the germanium. But later that germanium was replaced by silicon. So this is the first junction transistor made by William Shockley of Bell Lab. And Shockley made that junction transistor or sandwich part, like between a p-type and between two p-type or two n-type, an alternative material like a n-type or p-type material could have been sandwiched, and a transistor you can realize. So that junction transistor became the central device of the electronic age. There is no doubt about it. In 1947, this is the basic transistor idea, that if a input current is weak, a transistor can control a strong current. So this is the basic idea. With that idea, it has been discovered. So it has been already, these things has been told. 1958 integrated circuit. So this is in this figure you can see the Jack Kilby holding a chip in his hand, and a single device that contains interconnected array of elements all together in a single chip that we call a IC or integrated circuit. On the right hand side you can see what are the components within an IC, what are the plastic case, notch, basic the fundamental silicon chip or the most important silicon chip inside it. So why we celebrate the transistor today? Because the transistor plays a pervasive role in everyday's life, from morning to evening, everywhere. We require transistor, from car to mobile to laptop to PC, everywhere that is a transistor. So it can be considered, definitely it can be considered as the most important fundamental invention of 20th century. And it has been the driving force for microelectronics. Also, it has been the basic building block for IC and computers. Now, as a part of the member of IEEE Electron Device Society, so IEEE Electron Device Society is celebrating this transistor, invention of transistor during 2022 to 23 as the 75th anniversary of the transistor, which is one of the most important invention of our history. So as a result, I am also, as a part of IEEE Electron Device Society, we are also celebrating the transistor 75th anniversary. So this is the Jack Kilby, who has invented the integrated circuit, who was awarded Nobel Prize in Physics in 2000. Now we'll come after discussing the initial part, that is the brief history of the transistor. We'll discuss about the scaling concept and other things. So what is the problem with germanium? Germanium has suffered with some performance handicap. So basically that's why we have switched to, or the people have switched to silicon. So without silicon, that realization of IC wouldn't have been possible. So that's why later we have moved from germanium to silicon. So this is the starting processor of Intel 4004. And in 4004, it is based upon PMOS technology. It was introduced in 1971 with a clock speed of 700 Hz. Just think, it was the initial transistor by Intel was working at a speed of 700 Hz. And today we are dealing with at least few hundred gigahertz. Okay. So tens of gigahertz, not 100 actually, but tens of gigahertz range we are working today. So this is the improvement, or this is the revolution I was talking about. And the number of transistor, see the number of transistor. Initially, the transistor released by Intel in 71 was containing only 2,300 transistor. It is in hundreds, thousands, few thousands. Okay. Now it is in billion. Okay. So that is the revolution, or that is the technology improvement. That is that actually happened, and that is, we'll try to see those improvement, why that improvement occurs and what is the major force behind it, how that improvement occurred. We'll try to look after these things in this talk. So later they have realized, Intel, with a transistor called 8085, a famous transistor. We are every day in classroom we are dealing with it. It contains 6,500 transistor in 1976. So in 1976, from 1971 to 1976, in 5 years, from 2,300 transistor to 600, 500 transistor, they have done it. Okay. So they have achieved the number of transistors. They have increased the number of transistor almost double or thrice. Okay. 3 times. The number of transistor has been increased. So now consider the latest microprocessor introduced by Intel, that is the Core i9 processor, and see the number of transistor. It is named, the chip name is 14900K. So it contains 26 billion transistors. So just see the differences. Initial transistor was 2300. In 85, it is 6500. And now it is 26 billion transistor. Okay. So it is 26 billion transistor and the clock speed is 6 gigahertz. So initially it was 700 hertz and now it is 6 gigahertz. And Intel is the next processor of Intel will be based on the ribbon fed transistor, and which is slated to debut in 2024, but unfortunately that didn't happen. So maybe in 2025 they will release that ribbon pen, which will use the Intel 20 angstrom manufacturing process. And initially this Core i9 processor, it has used a FinFET technology and 14 nanometer FinFET technology or 11 nanometer FinFET technology they have used. And M1 Max, another processor, it used almost 57 billion. So see the number of changes. It is in thousands and it is in billions. So that is the improvement. That is the technology. That is the development of microelectronics technology. So Intel transistor technology will try to slowly or a little bit, will try to understand that transistor technology developed by Intel. So we are not considering the transistor before 2020. We'll start with 2021. So 2021, in quarter 1, 2, 3, 4, the type of transistor they are using is FinFET. So up to they have planned to use FinFET technology up to the second quarter of 2024, and then they have planned to replace it using a concept called ribbon FET. So up to till now, but unfortunately, as I told, that maybe that ribbon FET will be introduced later. So we are right now also they are relying on FinFET technology. So this FinFET technology basically uses 20. Finally, it was started with 11 nanometer FinFET technology. Later, that 7 nanometer FinFET technology was used, 4 nanometer, and finally they have plan to use 3 nanometer FinFET technology. And in future, in a ribbon FET technology, they are planning to use 20 angstrom technology. So that is the technological difference. See the device size or device dimension, how much it has been shrinked, how much it has been miniaturized, how much it has been scaled. Okay, so see that it's an amazing story. So Intel transistor technology, see 10 nanometer super fin technology, preliminary they have used. Right now they are using. From that, they have planned to use Intel 7 nanometer technology, FinFET technology already. Then 4 nanometer FinFET technology, and then finally 3 nanometer FinFET technology. And from that, they have planned to use ribbon FET with a power via concept for interconnection, obviously. That will be using 20 angstrom technology in future. So that is how the Intel is going to use or change their nodes or technology. So number of transistors. Let us consider the number of transistors. For that, we have taken two very common processor, or that one is Qualcomm Snapdragon processor, octa-core. This is a ARM64 mobile SoC, we can call it. Normally, we used to find it in mobile. It's a SoC, system on chip, and it is a basically ARM type processor, 64-bit ARM type processor. We call it Qualcomm Snapdragon processor commonly. It's a very popular processor. See the transistor count, 53 billion. And see the 8-core i7, 26 billion. It has been released in Qualcomm Snapdragon. That the one I am showing is, it has been introduced in 2017, and the 8-core Intel i7, it has been introduced in 2014. One is by Qualcomm, other is by Intel, and the process technology they are using is 10 nanometer, and Intel at that time in 2014, Intel was using 22 nanometer. And the area, 94 millimeter square, the total chip area. So it's basically very small. And the one Intel is using, it has an area of 355 millimeter square. So see the number of transistors or the number of MOSFET in a single chip. That almost always in a thin silicon. See the number of chip, and it's an amazing number. So number of transistors made and shipped so far in this world. So there is no such thing made by somebody else, okay, made by the human, and in so many, in so much, in a enormous number. It's a huge number, and this is the number, approximate. This is the approximately. This is the number. This is the number of the transistor so far made and shipped. So it's a huge number, and there is in competition to any other thing. This is perhaps the largest thing, largest number. So this is that you can say easily what human has done, what human has manufactured in largest number. The answer is transistor. So timeline of transistor development, I have already gone through this. And basically this slide is little bit hazy, so I'll not discuss about it. We'll discuss about it later during my talk. So how a transistor work, and I will not discuss about it in very much. So in transistor, you can say there is a terminal called source and there is a terminal called drain. So one terminal is responsible, or you can call it sometimes emitter and collector. So one terminal is responsible for the generation of carrier, and another terminal is responsible for collecting it, or it is the sink. So one is called source, another is called sink. So from one terminal, the carrier generates, and in the other terminal, the carrier goes, and in between there is a control terminal. That is perhaps the most important terminal, which sometimes is called as base, or sometimes it is called as gate, or in case of a triode, it is called as a grid. Okay, so transistor has too many application, but there are two basic functions. One is switching and one is modulation and amplification. So in the simplest sense, so to the one, those who are not from electronics background, how a transistor can work. So in order to explain that, we can say the transistor works like a dimmer. So dimmer means with a push the knob of the dimmer, the light comes on and off, similar to a switch. So rotate the knob back and forth, the light goes brighter, dimmer. So that's called a modulator. So a transistor also works like this. So in case of a switch, on and off. So if you apply the proper voltage at the control terminal, or if you supply a proper current to the control terminal, the transistor switches back and forth between the on state and the off state. That is called brighter and dimmer. So output will be either brighter or output high. A high current will obtain, or a very small current will obtain. We can call it in one case it is on, in other case it is called off. So that is a role of the modulator or role of the switch. So what is a transistor? Basically it's a switch. So there is a two terminal, as I told. One terminal is source, which is responsible for generation of the carrier, and one terminal is drain, which is responsible for collecting the carrier. And in between there is a terminal called gate, where we apply the voltage to control the flow of the carrier from source to the drain. And if that, by applying some voltage, and if that voltage is known as gate to source voltage, and if that gate to source voltage is larger than the threshold voltage, we can call the transistor is working in on state. So we can obtain the good amount of current in the drain terminal. On the other hand, so this is a MOS transistor. You can say the one side there is a gate, on the top it is gate, and the source and drain, they are interchangeable because MOSFET is a symmetrical device. So either one of them can be source, or either one of can be drain. Which one will be source and which one will be drain, that depends upon the voltage obtained. The lowest voltage or the lowest potential in a circuit is normally the source, treated as source. So this is a definition. I have already told that we can, a basic MOSFET is shown in the figure, a silicon-based MOSFET. On the right side, you can see the terminal called drain, or sometimes it is called collector, or sometimes it is called plate or anode. On the left-hand side, you can see the terminal called source, which is responsible for generation of the carrier, source or emitter or cathode. In between, the third terminal is known as gate or base or grid. In between, there is a silicon dioxide insulator, that MOSFET or metal oxide semiconductor, that is the oxide we are talking about. So how a transistor works, both the dimmer and transistor can control the current flow, there is no doubt about it. So both can act as a switch and as a modulator or amplifier. But the important difference is the dimmer is working by our hand. So it is hand-held or hand-operated device, and the transistor is operated by feeding some clock voltages or clock signal. So it is million times faster than our hand-operated device. So transistors are normally made of semiconductors such as silicon and germanium, gallium arsenide. So it is basically, it can be a transistor can be based upon a elemental semiconductor. It can be based upon a compound semiconductor. So this material can carry electricity not well enough to be conductor, but semiconductor, you know, it is between an insulator and conductor. Hence the name is semiconductor. So you can compare a transistor to a ordinary faucet. So water enters the faucet from the pipeline, in the pipeline from the water distributor, and then water leaves the faucet into the sink. So that is the drain terminal, other is the source terminal, and the water tap that controls the flow of the water is, we can call it the gate terminal. Transistor type, there are basically three types of transistor, or there are many more also. But MOS means metal oxide semiconductor, FET means field effect transistor. There is an alternative structure called as a bipolar junction transistor. Let us come to the Moore's law. So it is a basically observation made by Gordon Moore, where he predicted the number of transistors will be doubled in an integrated circuit after every 24 months. So at that density, that has also minimized the cost of a transistor. So basically that observation is a important observation, and the paper written by Gordon Moore regarding it, it's a basically economics based paper, and in the paper there is not such technical electronic technical content, but rather that economical part has been stressed and emphasized in a much better way rather than that electronic technical ideas. So where he has predicted that number of transistors will be doubled in every 24 months. Initially, that kind of prediction was actually fulfilled. Even actually up to 2000 or 2010, also this idea predicted by Gordon Moore, or the the observation made by Gordon Moore was satisfied and fulfilled. So after every 24 months, the number of transistors doubled. But later, as the transistor became much shorter, and as they have entered in the nano dimensional regime, that idea couldn't be fulfilled in future. So that's why we need to replace once the Moore's law, that is called the failure of Moore's law. Actually, the Moore's law failed in that case, and there comes the invention or the necessary technologies that is we'll talk about. So Moore's law is, as you can see, it's an exponential curve doubles after every 24 months or 2 years. So see the number of transistor in 4004. So in 4004, the number of transistor is in some thousands. In 8008, that is the first 8-bit transistor of the Intel released, then 8080, then 8086. See the number of transistor is in few 10,000s. See, then it is 286. Intel 286, it is in few lakhs. Intel 386, 1 lakh, about 1 lakh. For 286, it is about 1 lakh. For 386, it is about few lakhs. Intel 486, it is 10 lakh about. Then comes Pentium processor, Pentium 2, it comes then million. Okay, Pentium 4, billion, and then that trends actually succeeded and followed, and then it becomes a huge number of transistors actually followed, but up to that Intel Pentium 2 or so. So, and the technology used so far. From 2002, we have discussed in these slides. In 2002, the number of transistors is 2.6 million, and the technology node used is 180 nanometer. See, in 2004, as compared to 2002, the number of transistors almost doubled. See, it is 4.4 million. Well, instead of 2.6, the double is actually 5.2, but not exactly 5.2, it is 4.4. We can consider it as a double. So the the technology node is 130 nanometer. In 2006, the number of transistor is almost double again, 4.4 to 7.3, and the technology node has been changed from 130 nanometer to 90 nanometer. So in that sense, from 2008, it is 111.2, and the technology node used is 65 nanometer. And finally, in 2000, now the change is after 2010. So actually at C, up to 2010, so that the trend predicted by Gordon Moore was followed. That number of transistor was doubled or little bit close to double. Actually, it has been followed, and the technology has been decreased. Technology node has been decreased. It was started from 180 nanometer and it came to 40 nanometer. So number of transistor doubled. But what happened after 2010? See, after 2000, at 2012 also, the number of transistor almost doubled. But after 2012, see, the number of transistor couldn't be doubled. See, it is 20 million. In 2012, it is 20 million. In 2014 also, it is 20 million. In 2015, it has been decreased even by using 16 nanometer technology. It became 19 million. So that is the area where Moore's law started to failing. And in order to that support that historical cadence of the transistor scaling, or in order to support in order to continue that miniaturization, what are the technology changes we'd like to bring, or the people around the world they have brought? We'll discuss about it. So this is a figure or graph which shows the various eras initially. So 1900 to 1935, it has been, we can call it as electromechanical era. Then 1935 to 1945, it is the solid state relay era. In 1945 to 1955, it is called as a vacuum tube era. And from 1955 onwards to 1975 or so, it is called transistor era. And 1975 onwards, up to till now, it is called the integrated circuit era. So that is the first thing. And see the calculation made by per second by investing £1,000, $1,000. See, the number of operation or calculation made was also increasing, and it is growing exponentially. So initially we have used Hollerith tabulator or analytical engine, then IBM tabulator, then Colossus, Bell calculator. Then we have started to using in 1950s Univac, IBM 740 machine, PDP made by DSE, etc. Then in 1975, so Compact Desk Pro, IBM PC, those things came, and see the number of calculation made by that time, 10 to the power 6 or so. So 10 to the power 6 per second by investing $1,000. And see this graph shows up to code i7 or code 2 Duo. Then later, the number of operation calculation per second, it is growing up to human brain. It is crossing the human brain, mouse brain, and it is targeting the human brain. So the operation number of operation made by human brain is normally lies in the range of 10 to the power 15 or so. So it is targeting that. It is approaching that, and that's why that DNA computing and etc. they are coming on optical quantum technologies, and these things are coming in picture. This is the reason behind it. So see the difference made in this small year. So even in our case also, I have used my first mobile phone maybe in 2010 or so, or 2006 or so, and that is the Nokia phone, some 3110, etc. But nowadays, I am using I have already forgotten the phone I have used in that before 20 years. So can you? That's why I'm asking that question. Can you remember your first phone? See the technological changes made so far. So most I have already discussed. This is not visible. Okay. Transistor problem. So what is the problem with that transistor, or why that scaling or downscaling or that miniaturization couldn't be fulfilled actually? So density, increase of power density. So power plays a huge important role. So as the number of transistor, as we are putting more and more transistor in a single IC, as we are miniaturizing the size of the transistor, so basically we are putting more and more transistor. Everyone requires power. So power density increase. So to control that power density, it's a huge problem. So this is one of the huge area. Okay, so power, to handle the power. Device variability. You know that there is no two things in this world exactly identical. No two cricket balls are identical. No two footballs are identical. Even no two transistors are also identical. So they are all different. So, but the difference will play a very important role as the size of the transistor become less and less. So as the size of the transistor becomes 3 nanometer, 4 nanometer, such that, so number of electrons will be also very less. So in one case, see, suppose for one transistor, to make it in on state, suppose say 100 electrons are required. In another case, for other transistor, maybe made using the same technology at that same fabrication, using the same batch, maybe it requires 125 electron. So see the difference, 25% difference is there. But previously for a long channel transistor or previously for a large transistor, okay, so initial transistor, the number of electrons required to make it in on state is in the some 10 to the power 15 or so. So that maybe for other case it is, so for one transistor it is 10 to the power 15, 1 into 10 to the power 15. For other transistor it is 5 into 10 to the power 15. So difference is much, not that much. 1 into 10 to the power 15 and 5 into 10 to the power 15. The difference is doesn't much. So variability doesn't affect those transistors, but variability will have a huge impact, particularly for this transistor, that ultra scaled or nanodimensional transistor, particularly in the range of 3 nanometer, decananometer range, that is the 3 nanometer, 4 nanometer, 7 nanometer. This kind of transistor, the variability will play a huge important role, and that will impact the reliability of the transistor also. The transistor will be less reliable. They will not work properly. Similarly, so that will cause. So that is the reason, or one of the major problem area in a transistor. Complexity is another issue. Leakage is also definitely another issue. Power dissipation, that limits the device density. So device density is actually controlled by the power dissipation. So transistor will operate near ultimate limit of the size and quality. Eventually, no transistor can be fundamentally better that they even may come. So in this figure, we'll try to see what are the different transistor types actually. Okay, so there you can see three types of things are there. One is HPCMOS, one is LOPCMOS, one is LSTPCMOS. So what is HPCMOS? High performance. So we are trying to get high performance. High performance means we are concerned about the performance of the devices, but we are not concerned about the leakage. We are not concerned about the power. The power can be anything. We can sacrifice anything for the performance. So that is called high performance transistor. So normally they are used in server, router, where a high performance is required. It must work at a very high speed. So in order to make it a high speed, so high speed means the transistor should, in order to work for a transistor to operate in a very high speed, one of the fundamental thing is it should quickly charge and discharge. It should quickly charge and discharge the load. Load means in this case it will be a capacitor. So it should quickly charge a capacitor and the capacitor should be discharged quickly. So in order to charge the transistor quickly or charge the capacitor quickly, a high current is required. Capacitor is nothing but a water storage tank. So if a high water can flow, the tank will be filled quickly. So in a similar manner, if a high current flows, the capacitor, the load capacitance will be charged fully. So the on current should be very high. Leakage current. We are not worried about the leakage current. We are worried about the performance. We are not worried about the leakage current. We are basically concerned about the performance. So we are sacrificing the leakage current in order to get the high performance. So CV by I. CV by I is very important term. CV by I, the unit of CV by I is second. So basically lowest CV by I. So tau, it is sometimes we call it as a tau. So tau equal to CV by I. So tau, the unit of tau is second. So second, or the second is low. So basically normally the period is low, as it is lowest actually. So the frequency is highest. So it operates as a very high frequency. So that is the high HP transistor, HP CMOS transistor. The CMOS technology, we'll discuss about it. Then we'll come at the bottom, we can see another transistor which is called LSTP CMOS transistor. LSTP CMOS. LSTP means low standby power. So here the idea is we are concerned about the power. We are concerned about the leakage. We are not concerned about the performance. So basically we are sacrificing performance in order to get low power. So these devices should be low power devices. So they should be applied in case of like handheld devices like cellular phone, mobile, digital camera, etc. So So they are normally battery operated device. We don't expect that I will replace every day my camera or my mobile or cellular phone battery. Every day I will charge and every day I will replace it. So we basically expect that the more it longer sustains that power is good for us. So in this case, a very high frequency is not required. A very high performance is not required. A high frequency of operation is not required. The only thing required is a low power. So we want to minimize the power. So leakage current is lowest. See, lowest leakage in case of a LSTP CMOS. In contrast to HPC MOS, see high leakage, and it is low leakage, lowest leakage. But at the same time, in order to get lowest leakage, we are sacrificing the performance. So ion, in that case, HPC MOS, the ion is highest. But in this case, the on-state current, ion is lowest. So in that case, it will be lowest CB by I in case of HPC MOS. And in contrast, in LSTP CMOS, it is high CB by I. And so this is LSTP CMOS and HPC MOS. Now in between, there is another thing comes, LOP CMOS or low operational power CMOS. So it is just in the middle. It is just in the between HPC MOS and LSTP CMOS. It is basically we are not sacrificing the performance totally, or either neither we are sacrificing totally the leakage. So in between, the performance will be in between. So in that case, the ion will be medium, CB by I will be medium, leakage will be also medium. So this is C, on the left hand side, the y-axis, the operational frequency. In case of LSTP CMOS, they operate at a lower frequency, but HPC MOS, they operate at a higher frequency. And LOP CMOS, they normally operate at middle, in between HPC MOS and LSTP CMOS. And see the amount of subthreshold leakage, that actually the subthreshold leakage is limiting the downsizing, and the limit actually dictating the type of application where it has been used. So subthreshold leakage is the leakage, that lowest leakage, highest leakage, that is the thing we are talking about. And that leakage is basically the subthreshold leakage. So we know that MOSFET works if the gate to source voltage is higher than the threshold voltage. We know it. But below that VGS, so that is called technically, mathematically, we can call it VGS greater than equal to VT. But if VGS is less than VT also, then also MOSFET sometimes works. Okay. So that is called the subthreshold operation. And in that case, a huge amount of current or a large current also flows. And for one transistor, it may be very small, but for a billions of transistor, it is very high. It is a considerable amount of power it will draw. So that current will try to minimize, and that actually limits the type of the application where the devices has been used. So we considering these concepts, that multi-gate MOSFET structure has been evolved later. So actually, the technology was initially introduced as a double gate MOSFET. So instead of a single gate MOSFET, we are trying to use that double gate MOSFET. And from that, we are moving towards concept of FinFET and surrounding gate MOSFET. So what is double gate MOSFET instead of a single gate MOSFET? Basically, physically, you can explain this like considering that in a jail, basically one person is watched by one single policeman. The chance of escaping is very high. If instead of one single policeman, if that same person is covered by two policemen, then the chance of escaping is become less. And even it is covered by three police person, then the chance of escaping becomes much lesser. And if it is covered by everywhere, then the chance of escaping is much lower. So that is the concept. So basically, we know in a long channel MOSFET, it is the gate terminal is the terminal which actually controls the operation. So which involves to create an inversion layer underneath the channel. So it is the purpose of the gate terminal to introduce that inversion layer. So inversion layer is the basic thing required for a MOSFET to work properly. So that is, who is responsible for that? Gate terminal, one single gate terminal. So if that gate terminal has been instead of one single gate, if you replace it using two gate, then the chances of failure or misbehavior becomes less. Similarly, if the channel is controlled, if the channel is surrounded by the three areas, left, right, and top, then the chances of that misbehavior becomes much lesser. So that is called the FinFET. So FinFET is basically a multi-gate device and the three-terminal device. And if it is surrounded everywhere from every side, it is called a surrounding gate MOSFET. So basically, it is about the gate controllability. So it is the basically the how much the actually for a MOSFET to work properly, it is the gate terminal that should control the channel. But unfortunately, drain terminal will come into the picture also. For a short channel devices. For short channel devices, the drain terminal, ideally it should be controlled by the gate, but drain terminal will come into the picture and drain terminal will intervene. So actually that intervention should need to be minimized. So what is the way? We can increase the gate controllability. So better gate controllability is required. So in order to bring better gate controllability, and that better gate controllability could have been implemented instead of using a single gate, a multiple gate structure could have been used in order to achieve that better higher gate controllability. So as we introduce higher gate controllability by using multi-gate transistor, so obviously the short channel effect or SCEs, short channel effect SCEs will be reduced. And as a result, once the short channel effect is reduced, we can scale it or we can downsize it, we can shrink it in a better manner. So greater scalability will be achieved. And at the same time, low channel doping could have been also used, which will enhance the carrier mobility, because carrier mobility will depend upon the channel doping. For a higher channel doping, the rate of scattering will be large. As the scattering will be large, that carrier mobility will be raised. And if the carrier mobility is increased, I is proportional to mu. So if the mu is increased, the current drive would have been increased. And as the current drive would have been increased, then obviously it will occur at a higher frequency, because tau equal to CV by I. So if the I is at denominator, so if the denominator term is increasing, the tau will be decreasing. So we can the transistor can work at a higher frequency. So this is how this is the evolution of the multi-gate MOSFET structure. So this is the last decade of Moore's law. So Moore's law, foundation of Moore's law started with 0.7 per generation. But as I told, the feature size becomes very smaller, as the people started to diminish the size or downscale the size in a very rugged manner. So that's why that Moore's law failed. And as a result, various technologies like OPC, phase shifting mask, dual patterning, immersion lithography, everything comes into the picture. So last decade of Moore's law. So various disruptive invention. That is what I was talking about at the starting of my lecture, that that Moore's law failed. But in order to sustain that Moore's law, various disruptive invention or critical breakthroughs that time to time that has been introduced or that has been developed by various scientists around the world in order to sustain that Moore's law. What are those transistors? One technology is strained silicon transistor. So instead of using a normal silicon transistor, we are using a strained silicon transistor. So as a result of using that strained silicon, that mobility increases. And as you know, once mobility increases, that it can work at a high frequency. So what is the second important disruptive invention or critical breakthrough? That is, instead of using a normal silicon dioxide, we are using high K material or high K dielectric materials as a gate oxide. And moreover, instead of using that polysilicon as a gate material, we are again going back to the metal gate technology. So why those things are required? In order to reduce the gate leakage, or actually basically in order to reduce the short channel effect. What are the other things? The copper metallization, that has again came into the picture. Copper metallization. So initially, that metallization or that metallization technique was done by metal. Later, the metal has been replaced by polysilicon. Again, that metal technology or metal gate technology has been reintroduced, so that interconnect feature can be shrinked, because if the transistor is shrinking but the interconnect is not shrinking, then the overall performance will be the same. So we need to reduce the dimension of the transistor. At the same time, we need to reduce the dimension of the interconnect also. So interconnect should be scaled in the same manner as the transistor is shrinking. So in order to increase the routing density or shrinking interconnect feature, we use again that copper metallization technology. So this is a view from Intel, but unfortunately this view is only up to 2019. So initially you can see 2003, that is the 19 nanometer technology, silicon germanium, that was I was talking about, the strain transistor that has been introduced in 2003, then 2005 65 nanometer node, then to a 45 nanometer node. Actually, the node is 45 nanometer, but the gate length or the metallurgical gate length is 20 nanometer. This is a very important year in 2007, where the high K concept and metal gate concept again actually came. So high K technology, like high K material like hafnium dioxide, is introduced in 2007. Then in 2009, actually, Intel has moved to non-planar. So it up to 2007, it is a planar technology. But from 2009, it is non-planar technology. So non-planar tri-gate architecture they have introduced. And 22 nanometer in 2011, so FinFET technology. And maybe in 2015 to 2019, they have considered various technologies like carbon nanotube transistor, 3.5 devices, nanowire, etc. But unfortunately, none of them has been used as a commercial purpose by Intel. So commercially, none of them, neither carbon nanotube, neither 3.5 or nanowire has been used by Intel. But this has been the research area. So this is the end of roadmap quest for beyond silicon MOS era, CMOS era. So this year Moore's law turns 50. So it may not like to be more than 60. The physics involved behind the fundamental physics, the fundamental limit that actually involved is controlling the limit. So once Moore himself said in 2010 that once the transistors sink so small that they are means they are comparable to the size of the individual atoms, you cannot go any far smaller. So that era has already came. So the CEO of Intel, Stacy Smith, he said that Intel can see ahead of only a couple more generation in chip making technology. Beyond that, there is no more. But nowadays, so by looking at these slides, you may feel that then what is the future? So it cannot, can't we go more smaller? Can't we reduce the size? So is it the end? No, it is not the end. We'll see after it. So there comes another technology, more than Moore concept. So after the Moore's law, here comes the more than Moore technology. So it is basically the extension of the functionality of the CMOS circuits by integrating with the other technologies, and it is commonly known as the more than Moore technology. So basically, it's a culmination or it's a combination of CMOS with other technologies. Suppose say in a typical chip, in a mobile chip, there is digital logic, there is analog logic, there is RF devices, there is a sensor, there is a camera, there is optical things, everything. So if you can fabricate all together in a same chip, so this is called a more than Moore concept. So from this more than Moore concept, actually the concept called SoC or system on chips evolves. So here comes the SoC, and then here come two terms are there, SoC and SOP. So if it is a combined in everything is combined in a single chip, that is called a SoC. And if it is if now several SoC, if they become stacked together on top of one another, it is called system on package. Okay, system on package, neither it is still not realized, but it is still in the research stage. But SoC has been realized commonly. You can say it in a TV, modern day TV, LED TV. In a previously in our TV, we can see that various ICs, various transistor, various passive electric components. We call it as circuit board is there, and all the things was there. The whole circuit was there. But nowadays, all the circuits, everything has been actually miniaturized, and they are contained or they have been integrated within a single IC. They are put in a single IC, and that IC is called SoC. So nowadays you cannot see in a modern day LED TV the whole circuit board. The whole circuit board has been replaced by a single IC, and so that integration of everything is called the SoC, where system on chip approach, where everything has been introduced or integrated together. So beyond Moore concept. So beyond Moore concept, new material and new operating principle. So another concept is there beyond Moore. So it is more than Moore, and this is beyond Moore. So beyond Moore concept is basically, it contains three parts. To introduce beyond Moore concept, the material will be changed. In SOC, we have not talked about that. We haven't told that. I haven't told that the material will be changed. But here we are changing the material. Okay. Here we are changing the technology. Okay. New operating principle. Operating principle will be changed. Suppose say some quantum mechanical approach has been used or ballistic transport has been used. Then the operating principle of the transistor will be changed. So that is called the beyond Moore concept. So this is the beyond Moore devices where low supply voltage is required and low power consumption will be preferred. And instead, dimensional scaling, as the dimensional scaling is reaching the fundamental physical limit, these things are required. So new the technology or the operating principle will be changed in a beyond Moore concept. So new material, new operating principle, that is called beyond Moore. And more than Moore means system on chip concept. So this is the beyond CMOS technologies. Beyond CMOS technology, so architecture-wise, let us see starting from architecture-wise. Architecture-wise, so this multi-core architecture is there, morphic architecture is there. So instead of a multi-core architecture or morphic, we can use a morphic architecture. Instead of a von Neumann technology, we can use quantum technology. Okay. Instead of analog digital signal, we can use quantum state. So instead of a normal CMOS devices, scale CMOS devices, we can rely on single electron transistor or quantum devices or spintronic devices or ferromagnetic devices. And material-wise, instead of a silicon, we can use material, carbon, germanium, etc. Okay. And state variable, according to state variable, normally till now the transistor, as a state variable of the transistor is electric charge. So instead of electric charge, a molecular state or a spin of quantum spin, that spin or phase state, those things could have been used. So this is the beyond CMOS technology. Architecture-wise, according to the data, representation of the data, or according to the devices, according to the material, and according to the state variable, the changes I have shown. So perceived role of beyond CMOS technology. So this beyond, actually that beyond CMOS technology and that more than Moore element will combine together, and they will actually combine together in order to make it a more Moore technology. And it's so that that is everything together will be called that extended CMOS technology. So in order to fulfill the functionality of the CMOS devices that we call as the extended CMOS technology, that more than Moore element and the beyond Moore element, both of them will contribute. So it's a combination of beyond Moore, beyond CMOS, more than Moore, so and more Moore. Whole thing will combine. They will combine and they will make it. We used to call it as the extended CMOS technology. So now we'll see the various computational variable for emerging nanoscale devices. So earlier, the variable for emerging nanoscale devices was charge, the QIV. Okay, and the example is CMOS, based normal CMOS, conventional CMOS, or TFET, tunnel FET, or various other types of FETs are there. Electron dipole based, so variable is P. Then that example is a FEFET, or this is a ferroelectric device. Magnetic dipole, so it is depending on the spin of the current or magnetic material. So this is basically that they are the CMOS structure or CMOS nanowire molecular structure. Orbital state. So the variable is Bose-Condensate variable. So there is the example is BISFET. So the figure is there also. The first device is based upon the charge. The second one is based upon the electric dipole. The third one is depending on the magnetic dipole, and fourth one is orbital state. So basically they are the example of a beyond CMOS technologies. Beyond CMOS technologies, where normally the charge was used previously for the last 75 years or so, but the charge has been replaced using the other type of variable like electric dipole, magnetic dipole, orbital state, etc. would have been used to replace the transistor or to fulfill the functionality of a transistor. So in this same manner, based upon this physical phenomenon, that nano devices could have been classified, the emerging nano devices could have been classified into three types: electrical dependent, magnetic dependent, and mechanical dependent. So let us talk about some electrical dependent nano devices. So electrical dependent emerging nano devices. So emerging electrical nano devices could have been classified into three types. One, the one which is based upon ballistic transport, the one which is based upon quantum mechanical tunneling, the one which is based upon electrostatic. So electrostatic is the previous one which have been used previously for the first 50 years or so. So that we are trying to replace using tunneling based or quantum mechanical based way or ballistic transport based physical phenomena based devices will try to replace or has a plan to replace the conventional electrostatics based nano devices. So we'll discuss about the ballistic transport based nano devices. So ballistic transport, as we know, where the gate length or the length between the source and the drain is less than the mean free length. Mean free length means mean free length between two successive collision. So two successive collision of two electrons. So if L is less than lambda, in that case the ballistic transport occurs. If L is very large than lambda, very larger than lambda, then it is called diffusive transport, and L is comparable to lambda, then it is called a quasi-ballistic transport, and if its L is less than lambda, then it is called ballistic transport. And in that figure you can see, in that ballistic transport based devices, there is no collision, there is no scattering. So in diffusive transport there is a problem of scattering. So as a result, mobility decreases. Once mobility decreases, ion decreases. But in a ballistic transport, the mobility is very high. There is no collision. Ballistically, it reaches from source to the drain. So that is why they have a very they will provide a very high on current, and the mobility will be very less. So normally the use of this transistor, so without resistivity in a medium. So normally the example of such devices is carbon nanotube based phased, graphene nanotube based phased, or as a whole graphene based phased, and nanowire FET. The nanowire FET are also example of that. So I have talked about the advantages, but we should also discuss about the disadvantages. What are the disadvantages? Inability to accurately determine the size of the material and imprecise control technique while placing them on a substrate. So it is very difficult to fabricate carbon nanotube. It is very difficult to fabricate graphene. It is very difficult to operate at room temperature. That is a big problem. So room temperature operation is a very problem, and accurate fabrication is a difficult problem. Still people are working around it. Still many researchers are working around it, but maybe in future they will try to replace, they're aiming to try to replace the conventional MOSFET by using those transistor, ballistic transport based devices. Second type is electrostatic based nano devices. Electrostatics. It is basically called as a quantum dot cellular automata, EQCA. The interconnection of electron happens in the presence of electric field. So we use that quantum dot. So quantum dots are arranged in such a way, by arranging that quantum dot or cellular array pattern, we are trying to implement that Boolean logic function. So basically simplified interconnection, that is the advantage. Low power delay product, that is the another important advantage. But let us look at the disadvantages. The cryogenic temperature is required. Very low operating temperature is required. Still now. So still now, there is no solution of it, and proper synchronization is required among these quantum dots. So still now no viable solution has been obtained in order to solve this. So this is the second type of devices, electrostatic based nano devices, also aiming to replace the conventional MOSFET, but there are some problems also. Let us talk about some magnetic dependent nano devices. Magnetic dependent nano devices could have been classified into two types: magnetostatic based devices and spin transport based devices. So once it is called MQCA, like so quantum dot cellular automata or electrostatic based nano devices. So the alternative structure is MQ based CA. But again, the major problem is the mass production. See, the mass production is questionable. So there is a questionability about the mass production of MQ based CA, MQCA based devices. So they normally, and the advantage is they can operate at a very harsh operating condition suitable for military and space application. Okay, so that is the advantage, but the disadvantage is mass production is a disadvantage. So this is about MQCA. Spin-based nano devices, they are very attractive, and they have attracted a lot of researchers around the world. Okay, so the spin field of a transistor or spin FET. So the spin polarized electron transportation can be maintained by the magnetic field. So using magnetic field, basically we are trying to control that spin polarized electron transportation. So the advantage is it resembles CMOS circuit. So the CMOS circuit, so that circuit structure or circuit circuit technology are same as CMOS. So this is an advantage, but disadvantage. Look at the disadvantage: difficult fabrication process. Again, so fabrication process is questionable. So questionability regarding the mass fabrication. So that is the problem about the spin phase nano devices. Again, another type is mechanical dependent nano devices. You know the name structure. Instead of names, people are nowadays trying to obtain the names. Nano electromechanical structure. So these nano electromechanical structures are basically can be considered as mechanical dependent nano devices. Advantages is molecular characteristics such as small, uniform, self-assembled, but the problem is the realization into electronic devices package is a significant problem. CMOS structure, CMOS nanomolecular structure is such a is an example of the mechanical based nano devices. Tunneling based nano device. So these are the devices which depends upon the quantum mechanical tunneling. Tunneling is a quantum mechanical phenomena. So tunnel single electron transistor, resonant tunneling diode. Hello.
Sir, we are unable to see your presentation, sir.
Okay.
Sorry to disturb you.
Okay, just a minute. I will let us first. I will switch off my camera. Okay. Visible?
No, sir. Only sir's photo is visible to us, sir.
Okay. Can you see now?
No, sir.
No, no.
No, sir.
Sir, it is not visible.
Okay, just a minute. I'll replace my internet connection. Okay. I'll replace the internet connection and let us try again. Okay, I'll replace my internet connection. Wi-Fi setting. Maybe the package has been gone. Just a minute. I have almost finished. Just a minute. I'll try to connect with my mobile internet. Okay. We will try again.
So now your screen is visible, sir.
Now it is visible and audible also, right?
Yes, sir. Thank you, sir. No, I think we are unable to see it, sir. It is not audible, sir.
Yeah, can you hear me now?
Yeah, it is audible, sir, but your screen is not shared.
Okay. I'm just a minute. I'll share it. Okay.
Yeah, it is okay, sir. No, thank you.
Yeah. Just a minute. So I was talking about this tunneling based nano devices. So these tunneling based nano devices, the example of tunneling based nano devices are tunnel FET, single electron transistor, resonant tunneling diode. So basically they use as quantum mechanical tunneling as a basic operation behind it to work successfully as a transistor. So the electron, you know that normally the electron cannot pass a potential barrier, but according to quantum mechanical phenomena, if the quantum barrier is low and if the thin of if the barrier height is low and if the thickness of the barrier or the width of the barrier is small, then the electron can pass to the barrier due to that quantum mechanical phenomenon as a wave function. So the advantage is very small, fast and scalable, but again there is a problem. The major problem is low fan out. That is the current obtained by the quantum mechanical tunneling is very less. The quantum mechanical tunneling, as a result of quantum mechanical tunneling, we normally obtain very feeble current, very less amount of carrier. So less amount of carrier means they contribute to less amount of feeble amount of current. So as a result, low fan out occurs. large threshold voltage variation. So the device variability plays a huge role in this case, and they are very susceptible to noise, particularly at a low voltage. So these are the problem of tunneling based nano devices, and that's why the no company around the world is using these technologies. They are all considered as emerging nanoscale technology. Nobody has used it commercially. This has been already. So this is the input characteristics of various switching devices. You can see on the left hand side, on the y-axis, there is a drain current, and on the x-axis, there is a gate voltage. You can see where the tunnel FET places, where the MOSFET places, where the NC FET places, where the impact attenuation FET places, where the NMOS NEM's relay, means nano electromechanical structures relay, has been placed. So the future of the transistor. So the future of the transistor may be lying in the molecular electronics. It may lies in the carbon nanotube transistor. It may lies in the nanowire transistor. It may lies in the quantum computing. So nobody can accurately know. Nobody can predict where it is lying. And the CMOS devices will add a functionality to CMOS non-volatile memory, optoelectronic sensing, etc. So they will all combine. They will all culminate. So that CMOS technology will address new market microelectronics and bioelectronic devices. So at the same time, the macroelectronic devices or biomedical devices has been popping up, and this particularly those adiabatic logic and etc. These are they are getting highly popular. So those things are also must be considered. And biology, maybe that the biology may provide the possible inspiration for the new technologies and for bottom-up assembly and human intelligence, etc. So here, this is now 7:15. So I will discuss for the past 1.5 past 75 minutes. I was talking about things, and this is the possible further resources, or basically the bibliography which I have been used. So now it's time for discussion. So for any question, the last 15 minutes, I would like to contribute to question and discussion. So you are free to ask any question as per your wish. Okay. So please, I am ready to answer the questions. Okay. So please ask any question without hesitation. I'll try to answer it. Okay. I cannot guarantee that I will be answering it. I'll be able to answer it, but I'll try to answer it if possible. Please.
Good evening, sir.
Yeah, good evening.
Sir, this is Sudhir Raja from Warangal. I'm speaking.
Okay.
Sir, actually, I have a small doubt regarding while we are publishing some papers with respect to CMOS designing.
Okay.
People are asking for the real-time results. So we are going for the IC fabrication, and then we are getting real-time results.
Okay.
So that is not a problem because we can fabricate the chip. But at the same time, when we are trying to develop some applications using quantum cellular automata like QCA, EQCA, most of the publications are asking how far you will validate your results with your since they don't have any fabrication like that. Sir, how can we cope up with this problem, sir?
Yeah, the major problem of quantum dot cellular automata is that actually they require as I told, they require cryogenic operation. They operate at almost 0 degree Kelvin or absolute zero temperature, actually, till now. Now it is very difficult to fabricate or this, particularly in India. Now these quantum dots, actually it is difficult to fabricate quantum dot only, and that quantum dot cellular automata, it is very difficult to fabricate in India and realize it in India, particularly to achieve that cryogenic operation, etc. So for that, what I need to suggest is you must cooperate or you must contact with some other groups, particularly those who are working in Europe or so. Okay. So you may contact them and you must collaborate with them in order to get the actual result, where it is they have a facility to actually fabricate it and implement it. Not that they will fabricate everything or all the operation, all the chips which you have designed, they have fabricate, but at least they will try They have fabricated some of them. One of my friend actually is also working in quantum dot cellular automata, and he have also already collaborated with IMEC Belgium. Okay, contacted some guy. Actually, his name is Arnab. He's from. He contacted him, and they work together. Okay, they have made some. Yeah, and that is how you can solve your problem. There is no other feasible solution right now coming in my mind.
Thank you, sir. Thank you very much.
Thank you, Sudhir. Anybody else? Yeah, don't be afraid. Please ask me without freely ask me. You can ask anything. Okay, no problem. Okay. Any question you can ask. There are many participants I can see. Okay. So I don't know how you have liked my presentation or whether I have satisfied. You are satisfied or not? I don't know. Okay. Okay, then I'll try to request the moderator to conclude the session. Okay. If there is no other question.
Yes, sir, I'm there. Sure, sir. Thank you. Good evening, everyone. I'm Shubhra Baroi, Assistant HR at Abacus Institute of Engineering and Management. It's an honor and a privilege to express our heartfelt gratitude to Dr. Anshuman Sarkar, Professor and Head of Electronics and Communication Engineering at Kolani Government Engineering College, for gracing this occasion with his presence and sharing his valuable insights. Sir, we are deeply grateful for the time you have taken out of your busy schedule to enlighten us with your expertise. Your words have not only enriched our knowledge, but have also motivated us to strive for greater heights in our academic and professional journeys. And we look forward to more opportunities to learn from your wisdom in the future. Thank you very much, sir. Have a great evening.
Yeah, thank you, Shubhra. I will also wish a grand success of this particular program, and in future, I hope that you will continue to do so, organizing such lecture program to which will be fruitful and productive for all the participants. Thank you all.
Definitely, sir. Thank you very much for your best wishes. Thank you.
So with your permission, I am leaving. Okay.
Sure, sir.
Thank you,
Definitely.
sir. Thank you.
Nearer. এটা কি 1 থেকে 1.5 ঘন্টা, তাই তো সেশনটা?
হ্যাঁ স্যার, 1 থেকে 1.5 ঘন্টা।
এটা কি এর পরেও, মানে এর পরে কি সেশন আছে 9টার পরেও?
আজকে নেই স্যার।
আজকে নেই।